Okay, where we left off was at section 20.4, the preparation of carboxylic acids, and we've already learned a few ways to make carboxylic acids that were covered in earlier chapters. A couple of them are shown here. Let's see, what's the first thing? I think the first way that we ever saw how to make a carboxylic acid was from the oxidative cleavage of an alkyne. So oxidative cleavage of an alkene involves ozone followed by dimethyl sulfide or DMS, but the oxidative cleavage of an alkyne involves ozone followed by treatment with water, and we can end up with a pair of carboxylic acids. Then we talked about the oxidation of a primary alcohol, and what seems to be his favorite way of oxidizing a primary alcohol is to use sodium dichromate, sulfuric acid, and water. However, there is another set of conditions that we can use. If we want to do the reaction in base, we can treat it with potassium permanganate in water and heat that up. And then in the second step, we treat that with H3O plus. So that's the other option for that one. And then we talked about benzylic oxidation. So benzylic oxidation, and the same thing, we'll put here or, same thing, you could use the potassium permanganate to do that oxidation as well. So those are some of the ways that we learned. Another way, which isn't mentioned on here, but it just popped into my head, we talked about it earlier today, was the hydrolysis of a cyanohydrin. So if we make a cyanohydrin using potassium cyanide and HCl, that looks like this. So we have our hydroxyl, and then we have our nitrile. We saw that you can take this and treat it with H3O plus and heat it up, and you can make a carboxyl group or a carboxylic acid that way. So that's another way. And that's everything that I can think of that we've learned, every method that we've learned to make a carboxylic acid. However, there are other ways. Oh, it turns out I had it on my slide right here. Okay, so hydrolysis of a nitrile. Yes, using a cyanohydrin or just hydrolyzing a nitrile, any nitrile with H3O plus and heat, that will produce the carboxylic acid. Something I just want to mention about this is that the mechanism for this isn't shown in this section of the textbook, but it is coming up later. Okay, so I will show you the mechanism of this reaction, probably, well, not until later on in the chapter. And so what's cool about the hydrolysis of a nitrile, this reaction here, is that if you have something like, benzyl bromide, which is a primary, well, this is benzyl bromide, or any kind of primary alkyl halide, you can do an SN2 with cyanide. So you could just treat it with KCN, so you have your cyanide, and then you've added a carbon, and you can make a carboxyl group from that, which is pretty interesting. So it's a way to not only make a carboxylic acid, but you add a carbon to the initial electrophile in the process. And here is something that's completely new. I would say, totally new, and that is the carboxylation using a Grignard reagent. So we take a Grignard reagent, and what we do is we treat it with dry ice. So that's what this is right here. This is solid carbon dioxide or dry ice, either way. You can see the person is holding it with some kind of insulated gloves because it really hurts. If you let dry ice sit on your skin for too long, it'll burn it. Anyhow, so what happens is carbon dioxide, this is CO2 right here. This is just plain old CO2. Well, CO2 is a really good electrophile. So the Grignard reagent is a good nucleophile, so you're going to attack that, and you end up with a carboxylate. Well, a carboxylate is the conjugate base of a carboxylic acid, and thus we have to treat it with acid to make the carboxylic acid. So what you end up with is, let's say you had some kind of, alkyl halide, you would treat that first with magnesium to make the Grignard reagent, like this, I'll just say RMGBr. Then, if you treat that 1 with CO2 and 2 with aqueous acid, then you end up with a carboxylic acid, my friend. Now, of course, you're adding a carbon, but this is a new way to make a carboxylic acid. Very neat. And if you're wondering, well, how do you add the solid carbon dioxide? Isn't that a solid? What do? You've got a couple options. You can literally stir the reaction flask like this. So this is the step right here where you add the CO2. You can literally have your reaction flask like this where the reaction is stirring. in here, and then you could dump the solid CO2, just dump it right in there. Another option is that you can use CO2 gas and just let it bubble through there. But either way, that is a way to make a carboxylic acid using a Grignard reaction. Very cool way to make a carboxylic acid. So let's stop there. We've learned one really new way, the Grignard method of making a carboxylic acid. We discussed the hydrolysis of a nitrile right here, and then we looked over these other ways that we've studied to make carboxylic acids. So let's take all that and apply all those ideas and reactions to a question. It just says, identify the reagents that you would use to perform these transformations. So let's say we wanted to take ethanol and we want to convert it to acetic acid. So we're taking a primary alcohol and we're converting it to acetic acid. This means we're going to require a very strong oxidizing reagent. We're not changing the number of carbons. PCC won't work. Des-Martin periodinane won't work. The Swern reaction won't work. What is going to work? You got to bring out the big guns. You've either got to use sodium dichromate in sulfuric acid in water, or you can use basic conditions where you have KMNO4 or potassium permanganate, water. We heat that up, we get the carboxylate, and then the second step, we treat that with hydronium. Either one is going to work. Next one, let's see here. Oh, next one's a benzoic oxidation. We want to take toluene. Toluene, I'll just use my black pen. Toluene is just methylbenzene. And again, we're not adding any extra carbons. We're taking that and we're converting that to benzoic acid. So this is a benzylic oxidation. You could pencil that in there. Benzylic oxidation. This was covered way back in chapter 17, benzylic oxidation. So if we want to do a benzylic oxidation, what are we going to do? We treat it with sodium dichromate. It's one of the best ways to do a benzylic oxidation. So let me just copy and paste that. So we'll paste that in here. Oops. Just love this thing. There we go. Next one, we want to take benzene and convert it into benzoic acid. Well, that would be a synthesis, my friend. You know, to convert benzene into its carboxylic acid derivative, first we would have to brominate it using bromine and iron 3 bromide. All right. Then we can make the Grignard reagent by treating it with magnesium and diethyl ether. That's going to give us phenyl magnesium bromide, so MgBr. Then we're going to treat it with solid carbon dioxide, or just CO2, and then H3O plus, using the Grignard method of making a carboxylic acid, and that would give you benzoic acid. And the last one is 1-bromobutane. Jeepers, I put a lot of problems in here. 1-bromobutane. So let's see, 1, 2, 3, 4. 1-bromobutane, and we want to make pentanoic acid. Let's see here. 1, 2, 3, 4, 5. Let me draw it this way, maybe 1, 2, 3, 4, 5. Pentanoic acid. You could actually use this same strategy is here. You could treat it first with magnesium. So we could even pencil that in. You could do, you ready here? Number 1, magnesium. Number 2, CO2. And number 3, H3O plus. That would work. There are other ways to do it, though. You could, what's another way? This is a primary alkyl halide. So another way I would say is you could treat it with sodium cyanide, right? And that would do an SN2 to give you the nitrile. And then you just have to hydrolyze the nitrile, so H3O plus, and heat. Now we're really starting to see many ways, or not many, but maybe several ways that you can do synthesis. You know, a whole bunch of different ways that you can do some synthesis. Well, with all that in mind, let's move on and let's talk about reactions of carboxylic acids. And I'm going to teach you, I think, 2 new reactions before we get into talking about carboxylic acid derivatives. So 2 new reactions. We've covered a few new reactions today. I guess the Grignard synthesis of a carboxylic acid is new. But earlier on, we talked about lithium aluminum hydride reduction, didn't we? And we said that lithium aluminum hydride, let's write it down here, LAH can reduce ketones, aldehydes. It can also reduce esters and carboxylic acids, esters and carboxylic acids. And so if you take a carboxylic acid and you treat it with lithium aluminum hydride, which is a really powerful hydride delivery agent, but it's also, you could also view the hydride from the point of view as a base. You can convert the carboxylic acid after protonation with aqueous acid into a primary alcohol. Now this mechanism, I'll write it down here, mechanism is in book. Now I didn't write down exactly which mechanism it is, and I don't think I have it right here. Let me go up and find it. Oh, fiddlesticks, I had it here. Oh, here it is. Oh, it doesn't even say. It's just at the very beginning of section 20.5. It shows it to you, okay? I'm going to write here, will not ask. And you know that whenever I tell you I'm not going to ask you a mechanism, it's usually because it's not going to be found in any kind of ACS exam. I'm not going to ask it on a quiz, obviously, and I've never seen it in any kind of review materials for any kind of standardized exam, so I wouldn't worry about that mechanism at all. However, it is an important reaction to be able to reduce carboxylic acid to a primary alcohol. So a two-step process, and here is another way that we can reduce a carboxylic acid. It's using borane and THF. And here's a word I don't think we've used yet in this class. It's called chemoselective. Check this out. It says borane, BH3. So this is borane. Borane, BH3, can be used instead of LAH and is chemoselective for the carboxylic acid. So another way to reduce a carboxylic acid is just by treating it with borane and THF. Now, if you're wondering about the mechanism, I mean, you can look it up if you want, but mechanism is not even in the text. Mechanism not in text, therefore will not ask you anything about this mechanism. And you might be wondering, well, why do I have to know another way to reduce a carboxyl group? You just taught me a way to reduce a carboxyl group. The reason why borane and THF as a reducing agent is so cool is that it's specifically selective for carboxylic acids. Let's say we had this compound here. You've got two functional groups. You've got a ketone and you've got a carboxylic acid. If you were to treat that with LAH, that's going to reduce both of these groups. However, if you treat it with borane THF, the only thing that ends up getting reduced is the carboxylic acid, and the ketone stays completely intact. Now, if you're wondering, how does this thing remain untouched? Well, again, the mechanism I would say is beyond the scope of our course. It's just one of those reactions that you kind of have to know. And when I say kind of, I mean you have to know it. And yeah, it's something that you could look into if you want. But let's face it, there's quite a bit of content to know in this class already. Let's take a breather. Again, stop with the new material and just take a look at a question here and see if we can solve a synthesis problem. If you want to take bromobenzene and you want to make this compound, it's the same compound in both questions. This is called benzyl. This is called benzyl alcohol. And the reason I'm telling you the common name is because it can show up all the time in organic chemistry. Benzyl alcohol is really important compound. I'm going to go over to a blank document just so I have enough room to solve this thing. I don't want to try to squeeze everything into a page. I don't like that. So this is 20.11. A, we're taking bromobenzene, and we want to make benzyl alcohol. How would you do it? Well, let's see. Based on what we know, I think what they're trying to get at, as always, is could we apply one of the reactions that we just learned? And the answer is yes. If we could take bromobenzene and convert it into benzoic acid, right, which we already looked at a couple of times today, I think. If you had benzoic acid, then you could reduce this to benzyl alcohol using LAH followed by treatment with aqueous acid, or you could use borane and THF, either one. They're just trying to get you to practice that reaction. And so let's first make the benzoic acid. First, we treat this with magnesium in ether. That gives us the phenyl magnesium bromide. Check out the mechanism. Look, you have the carbanion, your magnesium bromide, okay? And what you're going to do is you're going to treat that with CO2. Instead of writing CO2, we're going to write out the whole Lewis structure, comme ça, as we say in French. And now the negative charge on our carbon is going to act as a nucleophile. The CO2 is an electrophile, and that's going to give us the carboxylate, right? We end up with a negative charge on our oxygen, like that. And so what do we need to do? We need to treat that with H3O plus in the second step, and that's going to give us benzoic acid. I'm just going to abbreviate the aromatic ring as pH, just to save a little bit of space. And then to get from the carboxylic acid to the primary alcohol, you can either treat it with LAH, followed by treatment with aqueous acid, or you could just throw borane and THF at it, and that will reduce the carboxyl group to the primary alcohol. Either way works. You're going to see this reaction come up quite a bit in organic chemistry, this whole making a carboxylic acid using a Grignard reagent. Let's try the next one. The next one's going to be a little different, isn't it? This is 20.11b, 2111b. Now we're taking toluene. So now we don't have to add a carbon. We've got toluene, and we want to make benzyl alcohol from it. Okay, we have that there. So I can think of a few ways to do this. I mean, the easiest way would be to take toluene and convert it directly into benzoic acid, which we just discussed. It's just benzylic oxidation. You could use sodium dichromate, sulfuric acid, and water. That's what we just talked about. And so, of course, then here you could just use borane and THF, or you could use LAH. Either one would totally work. There's other ways. I mean, instead of using this, you could use potassium permanganate in the first step, and H3O plus in the second step. You could use LAH here, followed by aqueous acid. You could even do, there's another way you could do this. You could take toluene and you could do a benzoic bromination. Why couldn't you do that? There's nothing wrong with that. You could just treat it with NBS. That will give you benzyl bromide of this compound. And then if you want benzyl alcohol, I mean, that's a really powerful electrophile. All you'd have to do is treat that with sodium hydroxide. Right? Hydroxide is a strong nucleophile, strong base. There's no beta proton. So the only thing you would get would be SN2 here. You wouldn't get anything else. There's no beta proton to even abstract. Well, there you have it, a little bit of synthesis problems. Any questions about those?
So I have a question. In the previous set of problems, you were going from benzene to benzoic acid, and you used a Grignard reagent. Could you have also done a Friedel-Crafts alkylation and then done this Na2Cr2O7?
Sure, yeah, you could do that. Yeah, so what you're saying is, could you have taken this, right, and treated this with methyl chloride and aluminum chloride to give you toluene, and then done a benzylic oxidation, right?
Right.
Yeah, I would accept that. I don't see why not. I mean, you're talking to a guy who's not a big Friedel-Crafts guy, but yeah, that would definitely work. I don't see why not. The thing about Friedel-Crafts, Caitlin, and I shouldn't be recording this and putting it on the internet, I don't think it's the greatest chemistry out there. I mean, it works, of course, and it can be optimized. But personally, and again, this is something you would never need to know this in 1,000 years, not while you're taking Chemistry 3111. Friedel-Crafts, in my opinion, this is really me telling you my opinion, but whatever, I'm entitled. Uh, it's one of those things I would avoid it if I could, but that's just me. It's like I worked with a fellow who, he said, I asked him, I said, is there any chemistry you don't like? And he said, oh, do you know what the Sandmeyer reaction is? I said, yeah, I know what the reaction is. I'll teach it to you later on this semester. He said, I've never gotten that thing to work in my life. So just a personal thing. All right, so now we get into carboxylic acid derivatives. So compounds that are related to carboxylic acids. Check it out here. It says, if you do the reduction of a carboxylic acid, you get a change in oxidation state. You could practice your oxidation states here. Okay, so the carbon, so I'm drawing this carbon here. The only electrons it would have would be an even split between the R group, right, and the carbon. And then the oxygen takes all of the electrons, and then this oxygen has every single electron. So you end up with 4 minus 1, which gives you plus 3. So the oxidation state of the carbon here is plus 3. Remember, reduction gains electrons reduced, or sorry, I'm in the States, it's reduction is gaining electrons. So that means we must reduce the oxidation number. So let's see here, you've got the carbon, you've got the R group, it's an even split there. The carbon takes all the electrons between it and the hydrogen, and then the oxygen takes all of the electrons. So then you've got 4 minus 5, which gives you negative 1. And there you go. So you're going from plus 3 to negative 1. You gained electrons. Therefore, that is a reduction. So whenever you reduce or convert the carboxyl group into an alcohol, it is clearly a reduction. Another way of viewing it besides the oxidation number is just by saying, okay, well, I thought you told me that if you gain hydrogens, it's considered a reduction. And I'd say, yeah, it is. Okay. Or if you lose oxygens, isn't that a reduction? Yes, that as well. However, we can't always, or I guess we can hitch our wagon to that most of the time. However, there's many reactions that carboxylic acids undergo where there's no change in oxidation state at all. And you can imagine by the tone of my voice that that's where we're going. We're going to be talking about taking carboxylic acids and converting them, or just studying carboxylic acid derivatives. So if your Z is a heteroatom, meaning it's not a carbon, if it's an oxygen or a halogen or a nitrogen, then there's no change in oxidation state. So it's not oxidation, it's not reduction. And here are the most common carboxylic acid derivatives that we are going to study. We're going to look at acid halides. Technically, if you have a chlorine, you would call this one an acid chloride. And you could have an acid bromide, of course. Then we have an acid anhydride, an ester, an amide, and a nitrile. And if you look at the oxidation state of the carbon in anything here, they're all plus 3. All plus 3. Every single carbon in here is plus 3. And we saw that the oxidation state of the carbon in a carboxylic acid was also plus 3. Again, that's why we call these carboxylic acid derivatives. And we're going to spend a lot of time talking about all of these. And you can imagine that some are more reactive than others. They do different reactions. They have some similarities and some differences. But let's talk about acid halides first. It says that acid halides, so acid halides were the ones where you had a halogen, and anhydrides are the one where you have an oxygen and another carbonyl bound to it. It says those are relatively unstable. And we don't tend to find acid anhalides or anhydrides in common naturally occurring compounds. However, esters and amides are everywhere in nature. If you've ever looked at that list of marketed compounds, marketed pharmaceuticals that I showed you one day, I mean, you'll find amides in everything, or in piles of compounds, and esters as well. If you are the kind of person who likes the smell of, fruits like strawberries and cherries and lemons and limes and oranges and, what else is on here? Pineapple, banana, and pear. Well, those fruity smells usually come from an ester. Even things like wintergreen. If you like the odor of wintergreen gum, that would come from an ester. So students will usually ask a question at this time, why can't we make more esters in the lab? Why can't we do that? Make, reactions where we get to have fun, things that smell good. Well, we do from time to time do labs where we make esters depending on the semester. Another place that you would find esters would be if you've ever studied waxes before. So esters are found in waxes like carnauba wax or beeswax, things like that. Earwax even, crayon wax, I don't know. Another place that you would find an ester would be a triglyceride. So triglyceride, if you've studied biology and you've seen a TGC or a triglyceride, those are also esters. Anyhow, if you're wondering about, these names like isopentyl acetate, methylbutanoate, where do those come from? We're going to get into that, but first, let's talk about how to name an acid halide. So, take a deep breath. Let's do it. Okay, here's what we do. To name an acid halide, if your suffix of your acid is ic acid, you replace it with il halide. And if the suffix of your acid is oic acid, you replace it with oil halide. Now, you're probably saying, aren't those the same because you still have an O here and an O here? It's true. However, I find it's easier to remember if you kind of throw both of those things out there. I'll show you what I mean. If you have acetic acid, again, that's the common name for a 2-carbon carboxylic acid, its acid bromide derivative would be acetyl bromide. Okay, so what if we gave it the systematic name? We would call this ethanoic acid, and you would call this ethanoyl chloride. Not dash, but ethanoyl chloride. I just find it easier to kind of think of both of them, but it depends on the person. All right, so we've got the common in the IUPAC. Benzoic acid becomes benzoyl chloride. I'm not even going to worry about the systematic name for that. What's another one? Like, let's say you had, I don't know, I'll just throw something else out at you. Let's say you had 7 carbons, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Let's say you had this. Let's say you had hexanoic acid, and you converted that to an acid chloride. 1, 2, 3, 4, 5, 6. You would call that hexanoyl chloride. All right. We talked about how to name carboxylic acids where the carboxyl group is on a ring. Well, the same thing would work there. Instead of calling it carboxylic acid, we call it a carbonyl chloride. Okay, so that's another one that you kind of have to just memorize the nuance. It goes from carboxylic acid to carbonyl chloride or bromide, what have you. Everybody with me on that one? Any questions about that? Then we're going to look at some examples. We will look at examples that go over this in detail, and there's lots of good problems in the book to practice naming. Acid chlorides and acid halides and acid anhydride, on the other hand, we replace the word acid in our suffix with anhydride. So if you have acetic acid, you have acetic anhydride. If you have succinic acid, you have succinic anhydride. Now you notice that this and this, they're both symmetrical. What do you do if you have an anhydride that's not asymmetrical? Well, in that case, you list the two acids in alphabetical order. So you put them in alphabetical order, A to Z. So this side would come from this acid, which would be benzoic acid. And then this side would come from acetic acid. And so you would call that acetic benzoic anhydride, right? You go from A to Z. All right. So there's that one. Let's say you had, you wanted to give the systematic name. So acetic acid, which would be ethanoic acid. So ethanoic acid. We would call this ethanoic anhydride. So ethanoic anhydride. Same old things over and over and over. Anhydride like that. For naming esters, esters are kind of interesting to name because what we do is we name the alkyl group that's attached to the sp3 hybridized oxygen first, and then we name the rest like it's the carboxylic acid, but we replace its suffix with from ic or oic acid to ate or oate, depending on the situation. So let's say you have acetic acid and you put an ethyl group where the hydrogen is, you call that ethyl acetate, right? This would be methanoic, methanoic acid. And so the systematic name would be ethyl methanoate, like that. Then we have malonic acid, so that would be diethyl malonate. Let's see, because you have two ethyl groups on there. Like, let's say I gave you something like, I'll just throw another one out here. Let's say we had this. We had an isopropyl group. Let me try to draw it the way these are all drawn. So let's say you had this, and then you had this. Okay, how would you name this? Well, first you name the group that's attached to the sp3 hybridized oxygen, so that would be isopropyl. And then you name this part as if it's a carboxylic acid, so propanoic acid, and it becomes propanoate. So this would be isopropyl propanoate, or you could call it isopropyl propionate if you wanted to use the common way of naming it. So common would be isopropyl propionate. That's why it's so important to know both the common and the systematic names of the first 5 carboxylic acids. Methanoic acetic, right? Methanoic formic, ethanoic acetic, propanoic propionic, butanoic butyric, pentanoic valeric. Okay, it's because they come up over and over and over. And then if you have your carboxyl group or your ester attached directly to a ring, then you name the alkyl group like before, methyl, and instead of calling it a carboxylic acid, you call it a carboxylate. So this would be methane cyclohexane carboxylate. Then if we look at naming amides, we're still not done. We got a couple more to go. For naming an amide, you replace the suffix ic acid or oic acid that we've seen coming up over and over with amide. So if we have acetic acid and we replace the hydroxyl with an NH2, it becomes acetamide or acetamide. I call it acetamide. So if we look at the systematic name, this would be ethanoic acid. And if you wanted to name this using systematic nomenclature, you would call this ethaneamide. All right, we've just replaced that oic acid with amide. Benzoic acid becomes benzamide. And we could come up with other examples, but let's just take a look at this one here. If you have the amide attached directly to a ring, we call it a carboxamide. So we've got carboxylates, we've got carboxylic acids, we've got, now we've got the carboxamide. So we would call this cyclohexane carboxamide. However, something that we have to look at with amides is that we can have primary, secondary, and tertiary amides. This amide and this amide, those are primary amides. Let me write this out for you. I covered this a little bit in Organic Chemistry 1 if you took it with me. But when you have 2 H's attached to your nitrogen in your amide, that's a primary amide. When you have 1 R group attached to the nitrogen and 1 hydrogen, we call that a secondary amide. Therefore, you can guess that when you have 2 R groups attached to the nitrogen, we call that a tertiary amide. So naming primary amides, we just simply give it the name of the acid, and we replace that ic or oic acid with amide. But when you have a secondary or a tertiary amide, it becomes a little more interesting because then you have to address the substituents that are attached to the nitrogen. Check it out. It says if the nitrogen atom of the amide bears an alkyl group, you have to give that name at the beginning, and we call it an N, or we provide the letter N as the locant. Now, it's normally italicized. You don't have to do that when you're practicing. let's say you have N-methyl, or you have one methyl, you would call it N-methyl. If you had two methyl groups, then you'd call it N-dimethyl. Now, something that's not on this slide is, what do you do if you have two different alkyl groups? Let's imagine we had this compound, let's say, son of a gun, just as I'm getting into it. There we go. Let's imagine you had this compound here, where you have a nitrogen that has a methyl and an ethyl group on it. In that case, you do it in alphabetical order, going from A to Z. So we have an N-methyl and an N-ethyl. Therefore, you would write N-ethyl, N-methyl acetamide. And you could also call it N-ethyl, N-methyl ethanamide. Either one would be perfectly fine. So instead of using acetamide, since it's got two carbons, you could call it ethanamide there, here, and here. All right, so that's how we name. This again would be a secondary amide. This would be a tertiary amide, and this would also be a tertiary amide, but it's got two different groups on it. All right, so let's see. What if we tried to name, oh, I know what I wanted to do. Talk to you about DMF. Do you remember back in Organic Chemistry 1, we talked about polar aprotic solvents, and one of them was DMF? It was this compound here. This compound here. So you can see the carboxylic acid that it comes from only has one carbon. So that would be formic acid, but it becomes formamide. And then we have two methyl groups on it. So the name of DMF stands for NN dimethyl, the two methyl groups, formamide. And you can see that from the acronym, we call it DMF. We don't call it DMM. We don't call it NN dimethyl methanamide. We call it NN dimethyl formamide. So that's further proof how common names are. If somebody was to say, hey, do you have a bottle of NN dimethyl methanamide? I would be able to figure out what they were saying, but I'd be like, that's a weird way of saying that. No, it's not weird, it's just not commonly used. Common names are called common for a reason, because organic chemists love them so darned much. Don't blame me. I didn't come up with them. It's just historical names for small compounds that chemists just never let go of. So we still use them to this day. And the last one, this is our last functional group that we learn how to name, is a nitrile. So nitriles, how do you name a nitrile? A nitrile, you replace the suffix ic or oic acid with onitrile. So if we have acetic acid and we replace the carboxyl group with a nitrile, it becomes acetonitrile. If you have benzoic acid, you replace this with a nitrile, it becomes benzonitrile. If you wanted to give it a common name, acetic acid, this would be, again, ethanoic acid. So this would be ethanonitrile. So ethanonitrile, like that. And that is it for all of the nomenclatures. So the next section, or the next question, is question 20.12, which has, we've got an anhydride, we've got an amide, we've got an ester, we've got another amide, we've got a nitrile, we've got another ester, and then we have another anhydride. I know that you just covered all of these with me, but I would like to take a short break so that everybody could at least try. See if they can go back in the notes and name even a couple of these, because if I just show you, that doesn't really help a ton. And then if you get tired of doing that, or you say, I want to try something maybe a little easier, usually, and I can't promise you this, but usually my students like or think that these questions are a little bit less complex. Or if you're given a name and you just got to draw the structure out because there's no name to come up with. The naming can be very complex. So I'd like to take a short break, get everybody to try question 20.12 and 20.13 if there's time. And then we'll go through them as a group. And then we're going to get into section 20.7, which deals with the reactivity of carboxylic acid derivatives. Let me show you something. If we scroll all the way to the end of the chapter, where am I here? Oops, I'm way ahead of myself. Where was I? You can see that in this chapter, we learn a whole bunch of different reactions. What did we just cover? We covered the nomenclature of acid chlorides, anhydrides, esters, amides, and nitriles. And that's why we have to know how to name those compounds to get through the chapter. You know, you shouldn't be talking about organic compounds unless you have some idea about how they're named. And you can see that we're going to talk about a lot of reactions that involve all of those molecules. And so in order for us to really step into that and to understand, you know, what's going on, we have to be able to talk about the compounds in a way that we can understand what's going on. So what we'll do is we'll take a short break, we'll come back, we'll take a look at those questions, and then depending on how things go, where the heck was I? I'm all the way back here. I think that we might call it a day after we cover section 20.7. And the reason why is there's just a lot of content to digest with all of this nomenclature. And then I would like to go over this section with you so that you have, you know, some good background heading into the weekend as you read the remainder of the chapter.